Divide and conquer technique. I'm Efina and I'll be presenting you this topic. The topics of discussion in this presentation are: what is a divide and conquer technique? Two well-known divide and conquer technique examples, which are the merge sort and the quick sort. Divide and conquer algorithms work according to the following general plan. A problem is divided into several subproblems of the same type, ideally about equal size. Then the subproblems are solved. Typically, it is done recursively, though sometimes a different algorithm is employed, especially when subproblems become small enough. If necessary, the solutions to the subproblem are combined to get a solution to the original problem. Here is a flow graph representing the divide and conquer technique. Initially, a problem of size n is considered to be solved using divide and conquer technique. It is divided into two subproblems, subproblem 1 and subproblem 2, and each of size n by 2. The two subproblems are solved separately. Usually, the solution to the subproblem are arrived recursively. Then, the solutions of the subproblem are merged or combined to find the solution to the original problem. Merge sort is a perfect example of divide and conquer technique. It sorts a given array of n elements by dividing it into two equal halves and sorting each of them recursively and then merging the two sorted smaller arrays into a single sorted array. The algorithm given here receives a input unsorted array of orderable elements. The output of the merge sort algorithm is a sorted array in non-decreasing order. Initially, in this algorithm, the array is divided into two equal halves. Then, the algorithm recursively calls itself for the two halves of the array. Then, merge is performed for the smaller sorted arrays to get a single sorted array, which is the output of the algorithm. The merge algorithm, which is called from the merge sort algorithm, receives two smaller sorted array as input. It combines them into a single larger sorted array, and that will be the output of the merge algorithm. It reads each element of the smaller sorted array, compares them, and places them in the sorted order in the larger sorted array. And that will be the output of the merge algorithm. Here is an example of merge sort. An unsorted array is the input to merge sort, and it is divided recursively to two equal halves until it cannot be further divided. Then the indivisible subarrays are merged to form a smaller sorted subarrays, which are recursively merged to get the final sorted array. Let us do the time complexity analysis of the merge sort. From the given algorithm, the recurrence relation of the merge sort could be written as C of n equals twice of C of n by 2 plus C suffix merge of n. C suffix merge of n represents the time complexity of the merge function. The worst case recurrence relation is derived as C suffix worst of n equals twice C suffix worst of n by 2 plus n minus 1, where n minus 1 is the time complexity function of the merge function in the merge sort. So C suffix worst of n equals n multiplied by log n minus n plus 1. So applying the sum rule, the time complexity of the merge sort is given as big O of n log n. The next divide and conquer algorithm is the quicksort. Like any divide and conquer sorting algorithm, the quicksort also divides the array into partitions. The partition happens at the pivot element, and there are several partition algorithms that could be applied in a quicksort. In this presentation, we'll apply horse partition technique. In the horse partition technique, first the pivot element is selected in the array, which is usually the first element in the array. Then the sub-array are scanned at both ends, comparing the sub-array elements to the pivot. In the left to right scan, denoted by the index pointer I, starts with the second element. This can skip over elements that are smaller than the pivot and stops upon encountering the first element greater than or equal to the pivot. In the right to left scan, denoted by the index pointer j, starts with the last element of the subarray. This scan skips over elements that are larger than the pivot and stops on encountering the first element smaller than or equal to the pivot. After left to right scan and right to left scan stop, three situations may arise. The first situation is if scanning indices I and j have not crossed, that is, I is less than j, we simply exchange a of I and a of j and resume the scans by incrementing I and decrementing j respectively. The second situation is if the scanning indices have crossed over, that is, I greater than j, partition the subarray after exchanging the pivot with a of j. After the exchange, all the elements that are at the indices less than the pivot element are smaller than the pivot element, and all the elements that are at the indices greater than the pivot element are greater than the pivot element itself. The third situation is if the scanning indices stop while pointing to the same element, that is I equals j, the value they are pointing to must be equal to p. Thus, we have the subarray partitioned with the split position s equals I equals j. Here is the horse partition algorithm. The input to the horse partition algorithm is an unsorted array. The output of the horse partition algorithm are partitions of the array at pivot. The pivot element in this algorithm is selected as the first element in the unsorted array. I index is initialized as the first index of the array and j index is initialized as the last index of the array. I is incremented until a of I is greater than or equal to the pivot element, and j is decremented until a of j is less than or equal to the pivot element. A of I and a of j are then swapped. These three steps are repeated until I is greater than or equal to j. And finally, a of I is swapped with a of j, then a of j is swapped with the pivot element. The algorithm returns the index j representing the pivot element index, which will specify that the elements with indices less than j are lesser than the pivot, and the elements with indices greater than j are greater than the pivot. Here is the quicksort algorithm. The input to the quicksort algorithm is the unsorted array, and the output of the quicksort algorithm is the sorted array in non-decreasing order. The quicksort algorithm applies the host partition to the input array by dividing it into two partitions at the pivot element, and then applies host partition to each of the subarrays recursively, and then merges the smaller sorted partitions into a single sorted array. Here is an example of quicksort. The input to the quicksort is a 8-element array. The first element 5 is considered as the pivot element. The variable I is initialized to 1 and the variable j is initialized to 7. I is incremented one index after another until the element at the index represented by I is greater than the pivot. J is decremented one after another until the element represented by the index j is less than the pivot. Then the elements at I and j are swapped. This happens until I is less than j. Then the element represented by j is swapped with the pivot element. Now all the elements that have indices less than the index of the pivot element are lesser than the pivot element, and all the numbers with indices greater than the index of the pivot element are greater than the pivot element. Now we have two partitions. Then the quicksort is applied to the two partitions recursively until the entire unsorted array is sorted. Let us do the time complexity analysis of quicksort. The recurrence relation of quicksort is C suffix best of n equals twice C suffix best of n by 2 plus n for n greater than 1, and C suffix best of 1 equals 0. Hence, applying the Master's theorem, we get the time complexity as theta of n log n. To summarize, in this presentation, we discussed about two algorithms that apply divide and conquer technique, which are the merge sort and the quicksort. Thank you.